Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with more physical metallurgy concepts with regard to phase diagrams. Binary phase diagrams, what happens to them when the immiscibility increases? The phase transformations with regard to phase diagrams, about how a solidification happens, let's say a gradual solidification, and certain special types of transformations called reactions. One particular reaction type we will see extensively today, that is eutectic reaction, and something about solubility. In the previous classes, we saw these ideas. Complete solubility in solid state, we called it miscibility, and we also saw about miscibility gap, where a small immiscibility happens below a certain temperature, and two phases, in this case alpha 1 and alpha 2, appear below a certain temperature. This is immiscibility. What happens with an increase in this immiscibility or in this miscibility gap? So miscibility gap widens and the single phase alpha region shrinks. If it increases further, then we may end up with a diagram like this, where we see alpha 1 and alpha 2 phases in two sides of the diagram, and no single alpha phase region throughout from left to right. So here at least there is some alpha region from left to right, but here there is nothing. So this kind of diagrams can come. And in this case it is alpha and alpha 2 which are presumably having single crystal structure, but it may be two different crystal structure phases also. This may be alpha, this can be this can be alpha, this can be beta as well. So what we end up with is more types of phase equilibria and phase transformation. So these are complex things, like there is a horizontal line here, it means something, it means a reaction is happening. Let's see about them in more detail in this class. So when it comes to phase transformations are controlled by several factors. For example, cooling rate is one factor. Depending on that, we end up seeing different types of phase transformations. But this is not part of phase diagram. So in this class, we will be approaching phase transformations through the phase diagrams. So phase diagrams indicate important fundamental characteristics of phase transformations. For example, does a phase transformation occur gradually or abruptly with respect to a small change in variables, for example, temperature? The temperature changes a little bit, the parent phase becomes the product phase abruptly, meaning entirely within that small increment in or decrement in temperature. Whereas in gradual transformations, it doesn't happen so. The product phase forms, but to only a tiny degree. Then how many phases are involved in a phase transformation? It may be one phase becoming another phase, or one phase transforms to more than one phases. So there are several types of transformations like this. So such aspects can be captured by phase diagrams. So let's look at one transformation, the gradual type, solidification in a simple isomorphous system. Let's look at that. So let's say this is our overall composition. Let's come down in temperature from a really high temperature. What happens when it touches the liquidus line, the orange line? What happens is liquid plus alpha forms, and let's put a tie line and see how much is the solid that has formed. So if you see alpha content, if you have to figure out, we need to measure the length opposite to this alpha phase and divide it by the total length according to lever rule, and what we will get is a very tiny amount of alpha. And when the temperature decreases one more step, let's say like this, we get slightly more amount of alpha. So this piece of the green line represents the amount of alpha, so that is increasing now. So if we reduce the temperature further, that amount keeps on increasing, and eventually when it touches this blue line or crosses the blue line, it becomes completely alpha. So if we look at what happens in the microstructure at this temperature, this is how the entire thing is liquid when it touches the just before touching the liquidus line, and when it crosses the liquidus line, there is some small amount of alpha that has formed, and as it cools down and comes to this region where it is crossing this, where it is about to cross the solidus line, you will have predominantly alpha phase, and once it crosses, it becomes completely alpha. So in this solidification, over the solidification range. So what we call as solidification range is the temperature range between this liquidus and solidus. The liquid gradually transforms to solid completely. That is, the liquid fraction decreases and the solid fraction increases at every step of temperature. There is one more transformation we will see, that is called precipitation. It has similar phase diagram features, but it is usually used for a solid forming from another solid. Okay. The transformation is gradual in that case also, but it need not be a complete replacement of parent phase by the product phase. Okay. It may be a partial parent transforming to product, and the product is like a precipitate inside the parent phase. So we will see about that in detail in future. Now comes one of the most important types of transformations called reactions. Horizontal lines in a phase diagram indicate reaction. Horizontal lines in a binary phase diagram indicate reactions. These are special types of transformations, but they are not like allotropic transformations or gradual solidification that we have just seen, or precipitation. Okay, let's look at one type of that. Okay, so that is the first type of reaction that we are going to see. So that is there in this phase diagram. So that is called eutectic reaction. In this, liquid becomes two solids. It's not one liquid transforming to a solid. It is liquid becoming two solids. Okay, liquid gives solid 1 plus solid 2. This reversible symbol is given here basically to say that when liquid is cooled, solid 1, solid 2 will form, and when solid 1 and solid 2 are heated, the liquid will form. It's a reversible reaction in that manner. Or more precisely, it is liquid and two solids stay in equilibrium. So this occurs at eutectic temperature. Here we are marking a eutectic temperature like this, TE. This is the eutectic temperature. That is the temperature at which this reaction will happen, and it will happen when the liquid has something called eutectic composition. So it is this CE labeled here, composition. This is eutectic composition. Liquid should have this composition to become the eutectic product, which is solid 1 plus solid 2. Okay. So this is a three-phase equilibrium, and its signature will be like this. A liquid is becoming two solids. So this sort of thing will be there in the phase diagram. You can one-to-one match and see here solid 1 and solid 2 will be alpha and beta in this phase diagram. So let's see where are they. So this part, this V sort of thing is here, and there is a beta here, and similarly we have this alpha phase, and it is going to look, and it is like this in the phase diagram, and the liquid is like this. Okay, so this signature you see, and the horizontal line here is also there, slightly longer. So this is the signature of an eutectic reaction. Now, so along this line in a binary system, three phases occur at equilibrium. As we already told, the reaction occurs at a fixed temperature, but more importantly, each phase has a fixed composition. These two are the compositions of alpha. This is composition of alpha, and this is composition of beta. Okay, and liquid's composition, we already called it as eutectic composition. That is the composition of liquid. So this liquid and two solids of these particular compositions stay in equilibrium. So that is the eutectic reaction. What happens in an overall composition of this sort? Okay, here. So at high temperature, it is going to be completely liquid, and when we decrease the temperature and enter into liquid plus beta region, we are going to have liquid and some beta. And as the temperature decreases, just above the eutectic line, what we are going to see is predominantly beta and some liquid. And then what happens if the line is crossed, all the liquid transforms to this sort of a mixture. This is, if we expand this part, we can see it is alpha beta alpha beta alpha beta. So this is two phases, and they occur in particular morphology and all. So this is not a universal thing. In many of the systems it happens like this. So this is called as eutectic mixture, and liquid transforms to this eutectic mixture below this eutectic temperature. This composition is called as hyper-eutectic composition because the overall composition here is beyond the eutectic composition. And in that composition, what we see is as the temperature decreases, we see that the beta phase content keeps increasing, but there is a small amount of liquid remaining, meaning the liquid gradually transforms to solid. It is beta, but only partially up to this temperature. We call that beta as pro-eutectic solid or pro-eutectic beta. Okay, and you can see there is some amount of liquid that is going to remain, this length by total length, that is the liquid content. That liquid is going to transform at eutectic temperature. All the remaining liquid transforms to alpha plus beta, that is the eutectic mixture. Often it is in lamellar form, the layered structure that we saw in the previous image. Hypoeutectic compositions are similar to this, but to the left of the eutectic composition. They have similar behavior. The pro-eutectic solid in this case will be alpha and not beta. You can see here it is alpha plus liquid when before touching the eutectic line. Exactly at eutectic composition, what happens? So if this is our overall composition, what happens? At eutectic temperature, so till this temperature it will be completely liquid. At eutectic temperature, the liquid transforms to alpha plus beta, that is 100% eutectic mixture. There is no pro-eutectic phase in this case. So similar to solidification of pure metal. So here I am talking about all liquid transforming to solids at one temperature. So that is similar to solidification of pure metal, isn't it? That is, it occurs at single temperature. All other AB compositions, all these composition, if you see, there is a range over which the solidification takes place. It's not a single temperature. For pure metals, it is a single temperature, all right. But in the alloy form, this eutectic composition that transforms from liquid to solid at one single temperature. That is an interesting characteristic of these reactions. Let's think about these ideas together. Let's understand systems with partial solubility. Okay, in solid state, there is only partial solubility, meaning the alpha phase here, beta phase is here, and the solubility of A in B and B in A is not complete. We don't see any single phase solid from left to right. So we say this is partial solubility. Okay, so alpha is a solid solution of B in A. Okay, so this A is like the solvent and B is dissolving in that, that is alpha, and this is the range over which alpha is stable, right? Similarly, beta is a solid solution of A in B. So B is the solvent here, so it is going to look like this. So in B, A can dissolve up to this much, that's the meaning. And these are also known as terminal solid solutions because they are in the terminal sides of phase diagram. Solubility limit changes with temperature, that can be seen by this line here. So as temperature increases, you can see solubility increases up to this temperature, then the solubility decreases. So this line is the Solvus line, this is the solubility limit, and that is moving like this, indicating that solubility limit changes with the temperature, right? And this is the solubility range. This is another term, or homogeneity range, or range of composition of one phase. So these words are interchangeably used. We saw that this kind of thing happens when immiscibility increases, or that miscibility gap increases. So what happens if it increases further? It becomes almost like this, right? So almost no solubility in solid state. This is how it can become. So still we can call alpha is a solid solution of B in A and beta is a solid solution of A in B, but solubility is extremely small. It was like this in the previous case, and now it is completely gone. That solubility range is vanished now. This kind of systems are also possible, and the signature of eutectic reaction is still there in this, but in the left hand side and right hand side, it's not like a V or something, it's like a straight line because barely there is any solubility for this phase. Now you can test your understanding with this. This is the aluminum silicon phase diagram. So from 0 to 100% silicon is varying in the x-axis, and it's a very simple eutectic system. There is nothing much. There are only three phases: liquid, alpha and beta, three phases, and in between them two phase regions are there, and there is a eutectic reaction happening in this. So try recognizing the pattern of eutectic reaction. Try recognizing which are the two solids. Must be very simple. It is alpha and beta. So alpha and beta are solid solutions of which element in which element, that you can think of, and which among these two has more homogeneity range or the solubility range. Stop, think about the answer and then play. Alpha phase is solid solution of silicon in aluminum. Beta phase is solid solution of aluminum in silicon. And alpha phase has more homogeneity range. You can see here there is at least a small range you can talk about for alpha. This small range is there, but for beta there is barely any solubility. For your understanding, I have made a zoomed in version of this phase diagram. You can see x-axis is from 99 to 100. Okay, so it is in the extreme high silicon ranges. If we zoom into that range, we can see a small beta region like this. So 99.8 and above, right? It means 0.2 is the kind of maximum solubility of aluminum in silicon. So that is beta. Now let's see some name conventions. This is extremely important because as we go along, we may be seeing different conventions. You should not be confused with all that. So this slide is especially for that. Now this is the diagram we have been seeing till now, calling the phases as alpha, beta, liquid and all. Okay, in the aluminum silicon system. ASM phase diagrams. ASM is American Society of Metals. Their phase diagrams are quite standard, and those phase diagrams have this sort of convention. You see, aluminum rich solid solution where silicon dissolves in aluminum, right? So this is the aluminum rich solid solution. The convention is like this. In bracket aluminum is written, not alpha. Okay. Similarly, in bracket silicon is written. This is how solid solutions are represented in ASM phase diagrams. And in CalFed software tools, it will be different. It's going to be like this. You see, the beta phase or the silicon rich solid solution is now called as diamond A4. That is the crystal structure of silicon. So that is used as the name for the phase itself. And here aluminum rich solution is called as FCC-A1. So FCC A1 phase and diamond A4 phase, these are the names. This A1 and A4 are called as structured by designations. This is also given for crystal structures. So that is used in the names. As we go along, you should not be confused with different terminologies. You should be able to understand what is what. Secondly, more importantly, how to look at a phase diagram and identify what phases are in equilibrium and is there any reaction. And you also will be able to think about how microstructure will look, and more importantly, inside each phase, how the atomistic picture will be. That training has already been given in the first few classes itself. Okay, so you should be able to think about all these things in this connected manner. That is going to help us a lot. Thank you. I hope the lecture is useful. See you in the next class.